we're going to cover how to calculate cooling loads. And then once you have your cooling load, you can figure out how much CFM is required. This is based on sensible heat. These are your sensible heat equations. So basically BTUs per hour we're going to figure out first. So from there we can determine on the second formula there how much CFM we're going to need for the room. And then once we know our indoor design temperature, that's our entering air temperature, and our supply air design temperature, which in this case we're going to use 55. So indoor design we're going to use 75, and leaving air temperature we're going to use 55. So basically sensible heat is a change in temperature. It has nothing to do with moisture. That would be latent heat. We're covering sensible heat and how to figure out CFM for the room. So basically there are four main contributors to sensible heat. One is people. People give off heat, and depending on the activity level, the amount of heat they give off changes. So the second item that contributes to the heat load for the building is lighting. How much lighting, what type of lighting, how many watts, the usage patterns, a lot of things go into it. We're going to make it very simple so you can understand. And then plug loads, computers, appliances, equipment, everything that generates heat within the building, it gives off and adds to the load. So the fourth is the solar load, that external sensible load. We're only going to deal with sensible, and that is radiation and conductance. And then we have infiltration that brings in some sensible load, but it's a small amount. It leaks in through the doors, through the window cracks. If you have a leaky building, then you're going to have more. But the newer buildings, they're a little bit more tighter now. So we're not going to cover infiltration. Just know that it's a very small amount. So basically the four major loads that add to your cooling load are the people, the lights, the plug loads, which is your equipment, appliances, and then your solar. These are sensible loads. This is how you figure the CFM on the sensible loads. So sensible heat from people, basically ASHRAE puts out an occupancy heat gain equivalency, and it's based on the type of activity. So you can see the first one here, seated, very light work, is only generating 230 BTUs. As the level of activity moves up, it's a little bit light work, not very light work, you burn a little bit more BTUs. You give off more heat. If you're doing heavy work and lifting, more strenuous work, then you're burning more BTUs. You're giving off more heat. So sensible heat from the lights. So basically 1 watt is equal to 3.41 BTUs. So we're not going to figure out usage factors, ballast allowances, and we're going to assume the CLF is 1 for now. So basically we just want to know how many watts of lights are burning, and then convert that into BTUs so that we can size our system and figure out the CFM. Same with plug load. We're just going to use a straight out wattage usage factor and multiply it by 3.41 BTUs to come up with the total BTUs. So then the solar or heat gain through glass occurs two ways. One is conductance. That is just basically based on the temperature difference between the indoor and outdoor temperature. And then the U value, which is the inverse of the resistance of the glass. So if you have real thin glass, real cheap thin glass, there's going to be a lot of heat gain through that glass. Nowadays they have high performance glass, they have double pane, triple pane, E-coatings, special glass to reduce the heat coming through the glass but allow you the visibility to see out of the glass. So there's conductance, and the other form of heat gain will be radiation. Basically that's the sun directly shining through the glass, and then there's the glass has its ability to retain heat and then give it off inside and outside. We won't get into all that. So here's your glass conductance load. So basically the difference between outside and inside, we will go over the equation for that, which is how to figure that. So basically, here's the equation for that. So the Q is your BTUs per hour. This is what you're going to come up to figure your load. So you do that for the glass or for walls, which we'll do in a minute. So your U factor is the reciprocal of your R value. R is the resistance. So the higher the R value, the greater the resistance, the smaller the U factor. The smaller the U factor, the less heat that gets through. So the greater the resistance, the smaller the U factor, the less the heat gets through. So you could say that basically the greater the resistance, the less heat gets through. So basically the equation is the U factor, which has to do with the resistance of the material, and then the area, A for area. So the square footage of the building component, so how many square feet of glass you have, and then the temperature difference between outdoors and indoor temperature. So the other way is radiation, direct and diffuse from the sun. So their equation is a little different. So Q again is your BTUs, which we're trying to determine. So it's based on how many square foot of glass times your glass shading coefficient, which ASHRAE has these in the book for those of you using ASHRAE. And it's affected by window blinds and Venetian blinds. And so there's different factors for that. And then your solar cooling load factor. Basically, this is dependent on orientation, south, east, west, north, and then your geographical location, the time of the day, and the month of the year. So how to calculate sensible load? These are the four major items that affect your load. So we're going to do a real quick load here. So let's say on people, we have the little bit of activity. They're burning 255 BTUs an hour. Let's say there's 2 people. So our people load is 510. So let's say this is a small office area. Let's say 20 by 10. So 200 square feet. We got 2 people in there. And then our lighting load, let's say we got 2 100-watt light bulbs. So 2 times 100, that gives us 200 watts. And then it's 3.41 BTUs per watt. That gives us a load for the lights of 682 BTUs. And then our plug load, let's say we got 2 of them at 125 watts each, 250 watts. That's 3.41 BTUs per watt. Multiply that by how many watts, and 853 BTUs. So you can see here, if you look at the watts, and I said we had 200 square feet, this would be equivalent to 1 watt per square foot, which isn't unrealistic. And this would be equivalent to a little over 1 watt per square foot. Then we have to add in our solar load. And to do that, we have to do a couple different calculations. So first we do the conductance. So we're going to say we have a U value of 0.8, which is pretty bad. Some of the double pane and the triple pane, you can get down into the 0.3, 0.15. So remember, the lower that number, the lower that U factor, the less load you're going to have on your building. So those real good glasses that they're developing now is going to reduce this number, which is going to reduce the BTUs that get through your building and have to be taken care of by your cooling system. So good glass will go a long way here. And that's what some of the energy retrofits, they do, they put films on glass or other things to make the performance better of the glass. So this 60 is the square footage. We're going to say we have 200 square feet of wall. We have 20 feet long wall, let's say, and 10 feet high. So we have 200 square feet of wall. And we're going to say 30% of that wall is glass. So 30 times 200 gives us 60 square feet. and then we're going to say our delta T between inside and outside temperature is 25. So that would make, since we said our inside is 75, that would make basically our outside design temperature at 100. So now we have to figure the radiation load from the sun, which is a different calculation. So basically, to figure out the BTUs, which we got here, 60, the area is the same for conductance calculation and irradiance calculation because the window area didn't change. So we got 60 square feet times our shading coefficient, point A, and then our solar cooling load factor, which we talked about is based on your orientation, north, south, west, east, the month, like where I'm at, July is pretty bad, July, August, and the time of day, 12 noon, 1 o'clock, 2 o'clock, and your geographical location, where you're located. In the United States, back east, on the west coast, in the south in Texas, or are you in Africa, South America, Canada? So your location makes a big difference. So calculating conductance through walls. It's basically the same as the conductance through the window, but we're not going to get into what the TD is temperature difference, and CL just takes into consideration the thermal capacity of the building to hold heat and then release it later on. But working with this delta T, it's just give you a good idea of how the equation works and how to figure your CFM. So now you got your conductance, like over here, like I showed you. So your resistance, the greater your resistance, the lower your U value, the lower the load on the building. So like here, your wall insulation, R13 is not as good as R19. So the more insulation you put in the wall, the less this heat's going to get through. The less this is going to get through, because that barrier for the heat to get through is going to be greater. The resistance is going to be greater. It means your U factor is going to be lower and less heat will get through. So in this case, our U factor is 0.07 and our area is 140. Remember, we had 200 square feet of exterior wall. We're just taking this wall here times the length. And we're minusing out the window area, which was 60 square feet. So we have 200 square feet of wall minus 60 square feet of window gives us 140 square feet of just wall, this type of wall. Now all walls have different resistances based on what it's made of. If this wall didn't have insulation, then boy, this heat would really come through. It'd be horrible. And then your temperature difference. Your 100 degrees outside design temperature and your 75 degree indoor temperature. Okay, so then adding all those up, those are all your sensible loads. Your people load, your light load, your plug load, your glass conductance, your glass radiation, and your wall load. That gives you a total of 15,490 BTUs per hour. Sensible. Now, how do you determine the CFM? Well, the equation we showed in the front, you take that equation and you just plug those numbers in. We know what our room design temperature is going to be. We know what our supply temperature is going to be. So we have all three values on the right side of this equation that we're missing. That can determine our CFM. So basically plug those in, do the math, and that will give you your CFM. Boom. 717 CFM we need for that room based on that load. So the only things we did not consider is what we talked about, infiltration. So that's the air that sneaks into the building from outdoors and brings its heat with it. It's a very small number. Older buildings, maybe they leak more, so that's a bigger number. And then latent heat. We didn't consider latent heat. People give off latent heat. Outside air, ventilation is required for the health of people. You got to bring ventilation in. We didn't consider that. That will be done at the coil. The coil will take care of the latent heat. The CFM will take care of the sensible heat. So we hope you like that. Please click and subscribe, and look forward to our next video.